Mike will be talking to us about maximally chaotic systems.
Yes.
All yours.
Oh, great. Thanks. Yeah. So I'm going to talk about this work I've done. Well, it came out fairly recently on systems of maximal quantum chaos. We started this quite a while ago, although we only finally finished it off a few months ago. So yeah, I'm Mike Blake. I'm currently at Bristol in the UK, which is, if you don't know what it is, it's a very nice city in the southwest of the country. And so this is on some work I did with Hongyu. And what we were interested in was we a couple of years ago actually proposed a description of chaos in quantum many-body systems that essentially was based on a theory of hydrodynamics. The idea, as I'll explain, was that it's the hydrodynamic degrees of freedom associated to the stress tensor that are responsible for many-body quantum chaos. And that was motivated by various results in, say, holographic systems or things like the SYK model. So at the time we developed that theory and we came up with various predictions and results of that theory that have been tested. But what I'm going to tell you about in this talk is some new results in which we now understand that this theory really describes maximally chaotic systems. So, and you can think of that, I think, as one of the distinguishing features of a maximally chaotic system is there's this hydrodynamic description of chaos in them. And then the second thing I want to discuss is various predictions of this theory or results we found through this theory that are actually very general features of maximally chaotic systems that we haven't actually really discussed so much in the literature at the moment, and I think are very surprising and something to really pay attention. I think means something quite deep, although exactly what I'm not entirely sure yet. So that's the basic idea. I'll start with a bit of quite general introduction, hopefully. Just I want to explain a bit of the background. And the basic idea is that we were interested and I am interested in understanding these new characteristics of talking about chaos in quantum many-body systems. So these have arisen over the last few years. Traditionally, it's been a very hard subject to try and quantify, to try and understand how ideas from classical chaos or single particle quantum mechanical chaos generalized to a many-body system. But over the last few years, people have come up with various new diagnostics of chaos, and one of which are these so-called out-of-time ordered correlation functions that perhaps you may have heard something about. So the basic idea is that there's been this large recent interest in chaos in many-body quantum systems, and there are these things called out-of-time ordered correlation functions, or OTOCs, which are basically just one probe of what is meant by chaos in a many-body quantum system. Okay. So roughly speaking, what do these various measures of chaos, what are they talking about? They're essentially interested in how operators evolve in time in a quantum system. And in particular, if I start with, say, some operator at an initial time, that's some simple few body operator, like, say, a Pauli spin in a spin chain, well, if I evolve it in time in the Heisenberg picture, it's going to become more and more complicated. And we're trying to probe that process of how the operator becomes more and more complicated and see what information and diagnostics of that process you can extract. So these out-of-time ordered correlation functions are one such probe. What they do is they say, take two operators that are initially at time t equals 0, just simple few body operators, like two different Pauli spins. But now evolve one of them in time in the Heisenberg picture, so it becomes complicated, and leave the other one alone as sort of a reference system. Okay. And then what you want to ask is to say, what happens is this commutator, as W becomes increasingly complicated, this initially starts off small, but it will grow with time. And so the growth of correlation commutators with time is a probe of this complexity increase in this operator. So to get something that we can measure, let's take the square of this and take its expectation value, thermal expectation value, or I'll always be using. And for instance, this, as I said, what happens is this typically grows, and you can make some nice statements about the growth of this in large N systems, such as holographic systems or large N quantum field theories, with many degrees of freedom per site. Then this starts off small and it grows, at least has a period of exponential growth with time. Okay. So this lambda here, which gives you this exponential growth in this out of time ordered correlator, is called a Lyapunov exponent, a quantum Lyapunov exponent, in analogy to how you get an exponential growth of divergence of trajectories in classical chaos parameterized by a Lyapunov exponent. This is an analog of that, at least in some sense, for quantum many-body systems. And one of the surprising things is that in a quantum many-body system, this can't be anything, but if you have a system at finite temperature, there's a bound on how quickly these types of correlation functions can grow. Okay. So in particular, they have to be less than or equal to this fundamental value here, which depends just on basically the temperature of your system. Okay. Good. So the question I want to ask, and I'm basically motivating this work, is what is special about systems that saturate this bound? So these systems for which they have this maximal volume, maximum Lyapunov exponent are so-called maximally chaotic. And the fact that they saturate this bound seems to suggest that something interesting is going on. And so then what is it that's going on in these systems for which they saturate this bound? Okay. So there are examples of these systems that are well known and well studied, explicit examples of maximally chaotic systems. So one is the SYK model at strong coupling, and another are holographic theories where the bulk description is a theory of classical gravity. Okay. And the basic general answer, or at least potential answer, that has emerged in various hints through the literature, and it's sort of implicit in studies of these models, and is what I want to emphasize, is that in these maximally chaotic systems, the chaos, this behavior, is hydrodynamic in nature. So what I mean by this is here just something very general, and I'll make the statement more specific as we go along. But here I just mean that this exponential growth in maximally chaotic systems originates from the dynamics of the stress tensor in the theory. Okay, so in particular, this exponential growth of these correlation functions is a result of interactions of these operators with stress tensor degrees of freedom, and that's something that actually, if you look explicitly at these examples of SYK or theories dual to classical gravity, in that case, this is indeed the case. In SYK, there's a so-called Schwarzian theory that parameterizes the stress tensor and is responsible for this exponential growth. In holographic systems dual to classical gravity, this comes from a gravitational interaction in the holographic system in the bulk, which in the boundary theory can be thought of as a stress tensor interaction. So these examples are consistent with this idea, but we want to claim this is a general and almost defining feature of maximal chaos. Okay. So in particular, because of these hints that and facts that in these maximally chaotic systems it's the stress tensor that's responsible for this behavior, in 2018 we used this as the starting point to build an effective theory description of chaos, so an effective field theory description of chaotic systems. And the motivation is as follows, which is that if the stress tensor is responsible for chaos, well, we have an effective field theory that describes the stress tensor. It's basically what's known as hydrodynamics. Okay. So the only difference between the hydrodynamic theory we use to build this description of chaos and the classical hydrodynamics you may have studied before, based on fluid mechanics types equations, is that we use something that's called quantum hydrodynamics, which is a framework that was developed over the last 10 years or so by Hongmu and collaborators and other groups as well, in which they were able to formulate a hydrodynamic description of the stress tensor that's actually valid at the full quantum level. So it elevates hydrodynamics to a quantum field theory with a path integral and an action and fields and everything. Okay, but it's still some effective description of just the stress tensor in that system. So in 2018, we used this quantum hydrodynamics to build an effective field theory of chaos, a general one just based on this hydrodynamic action, which I'll tell you a little bit more about. And using this hydro theory, we're able to consistently show that it's possible for this exponential behavior to originate from the stress tensor and couplings of operators to the stress tensor in a consistent way. And this theory led to certain predictions about connections between stress tensor properties and hydrodynamic phenomena and chaos, one of which is something called pole skipping. So this led to a new phenomenon based out of, it actually arose as a prediction of this theory, and also independently in some holographic calculations known as pole skipping. And this pole skipping statement is just, for us, I'm not going to talk about it in a huge amount of detail, it's now been well studied. It's a statement of just a precise connection between the exponential growth in these out of time ordered correlation functions and some analytic properties of the energy density Green's function in your quantum system. So this theory led to a prediction connecting the two, and this prediction has actually been proven to happen in basically all holographic theories in a paper that we wrote also in 2018, I think, or maybe 2017. No, 2018. Good.
Can I ask a question?
Yeah.
How is this EFT? Is this EFT related to the work of, for example, Moshe Razali? And
I'm literally just about to mention that. Yeah.
Oh, I see. Okay.
Yes. No. Exactly. So there are several. Basically, it's the same thing. Yes. So that's the technical details. I think there are some maybe slight differences, but morally, it's the same thing. So there are several explicit examples of this EFT. One is the Schwarzian theory in SYK, but exactly some of them, there are basically examples of this type of vector field theory constructed in 1+1 deconformal field theories by Moshe and Razali and Felix Hale and collaborators, and CFT and Rimner space. There's some slight differences in that they refer to the modes as reparameterization modes, reparameterization modes. But as we'll see, those are the same degrees of freedom that arise in this quantum hydrodynamic effective field theory. So they're basically the same thing is how I think. And in particular, this, for instance, this pole skipping phenomenon is in both. They're in both. Good. So so this was by these examples are mostly due to Razali and Hale, and I think some collaborators as well. Good. So this was where we got to in constructing this effective field theory in the past, and as far as I'm aware, this is the status of these examples. But what we discovered in this new work is two things, that one of which is maybe not surprising, but I think the other is. So further work has revealed two new features. So the first, which I won't talk about in a ton of detail, but I will explain why it's true, is that at the time we didn't know whether this, we motivated this theory by these maximally chaotic systems, but we didn't see any reason why, in general, there's no reason why this theory couldn't perhaps describe some or other systems as well, a hydrodynamic description of chaos. But actually, we now know that there's a self-consistency condition of this theory that actually forces the Lyapunov exponent to be the maximal value. So this hydrodynamic description of chaos is going to, or effective field theory description of chaos, this effective field theory certainly it applies to maximally chaotic systems, and so would predictions of it, such as pole skipping. So that might not be too surprising. I think there are general expectations that that should be the case, but it's nice that it comes out of the theory itself. And what's more surprising is that in this hydro EFT, and actually, as I'll explain more generally in maximally chaotic systems, something that initially seemed very strange happened, there's a suppression of exponential growth in out-of-time ordered correlation functions, which are these correlation functions built from commutator squares. So I'll distinguish commutator squares from out-of-time ordered correlation functions a bit as we go forward. But what I mean by this is that here I've written the correlation function, which is the square of a commutator. Now, if you expand this, you can expand this in terms of two out-of-time ordered correlation functions. When you multiply out the brackets, it looks like the sum of a correlation function which goes WV, WV, and then another one which goes VW, VW of T, V of 0, W of T. And the point is that in maximally chaotic systems, what you find is that each of these has exponential growth, but they're precisely out of phase with each other. So they have exponential growth that's precisely equal and opposite. And therefore, when you take the sum of these two correlation functions to compute this commutator square, you actually find at leading order in 1 over n, the exponential growth will cancel if you have a maximally chaotic system. Okay. And so this is something that's quite surprising. It immediately happens in this effective field theory and worried us for a while. But when we went back to the literature, we found that actually this is implicit and is true in all these examples of a maximally chaotic systems, like the Schwarzian theory or holographic systems dual to classical gravity. And so this you should think of, I think, as telling us something deep about what's going on in maximal chaos. You get this cancellation between these two correlation functions and a suppression of the commutator square, and it comes immediately out of this effective field theory, as I'll explain. Okay, good. So that was a relatively long introduction. So I'm going to review the EFT now, and I'm just going to review the basic ingredients, and really only the cartoon picture here is going to be important for what I say. So don't worry too much about the details. I just want to give you the spirit of it. And in order to do this in a kind of easy way, I'm going to suppose I'm talking about a 0 + 1 dimensional quantum system. So just time, no space, in order that I can do this sort of write equations down that don't look too bad. So the basic idea of the EFT is that we want to describe this growth of our operators in that time, or this, which is sometimes called the scrambling. And the way this is done is we essentially say we can attribute this to the interactions of these operators with some collective degree of freedom. So this is just words, but there are some, equations in the papers that explain what is meant by this. But the cartoon is that we have a coarse-grained description of this process of our operator getting more complicated, where if V of t is our operator that's getting more complicated, we think of it as consisting of two parts. It's some bare operator that, as time goes on, gets increasingly dressed by a hydrodynamic cloud from interactions with its hydrodynamic cloud. So we've got this cartoon of a bare operator, and as time goes on, it gets increasingly dressed with some hydrodynamic degrees of freedom. And that's some coarse-grained description of this operator evolving in time and becoming more complicated. Okay. So the key thing is not only, so that's the first step, we want to have this coarse-grained description of some coupling to some collective field. The next step is, this isn't just any field, it's actually the field that appears in this quantum hydrodynamics. Okay. So in particular, as I said, Hong and collaborators and other colleagues have done a lot of work on elevating hydrodynamics to the status of a quantum field theory. It's not too dissimilar to classical hydrodynamics in that you parameterize the dynamics of the stress tensor in terms of some other variables. In classical hydrodynamics, that'd be like a local fluid velocity or a local temperature. You do the same thing here in this quantum hydrodynamics, and they're just now variables that appear in some action and some quantum action. In this case, the variable that in 0 + 1 dimensions, the only variable you have is a variable sigma of t, which just tells you the time, the fluid time, local fluid time as a function of the physical time.
You want? Really?
So the basic idea is the key variable, the variable that appears in the action of this hydrodynamic theory and parameterizes in 1 dimension, 0 dimensions, the energy density. That's the only physical quantity. And there is some collective degree of freedom. It arises, you can show that this exists in the action as a consequence of energy conservation. And it's a reparameterized, you can think of it as the fluid time as a function of the physical time, or time reparameterization. So this is this reparameterization mode, basically, that also appears in these CFT descriptions. This is a reparameterization, time reparameterization of fluid time as a function of physical time. And then this quantum hydrodynamics just gives you some, gives you a framework for studying the dynamics of this collective field. It's got some action, and there are some rules. Okay, in a given system, this action will have a particular form. In general, there are some constraints and properties it always obeys, and you can construct it, for instance, as an effect. You can construct this effective action of this hydrodynamic variable. Okay. Okay, good. So the key point I want, okay, so this sigma of t is just our time reparameterization field that you introduce into your theory. But the reason this allows you to come up with a theory of chaos is that this variable sigma of t is not itself the thing you're interested in. It's not physical. What's important is the energy density and the stress properties of the stress tensor. And that's related to this field sigma, a bit like in normal hydrodynamics, through some constitutive relations. Essentially, it's some function of sigma and its derivatives and things like that. Okay. So ultimately, what we want to compute are properties of the stress tensor, not of the sigma. We just introduce sigma as a variable in the path integral. So stress tensor correlators can be computed from this action, once you know the action, and you've got this and the field in terms of the dynamics of this field. And this is just the same way that constitutive relations relate the stress tensor and energy, for instance, to the fluid velocity in normal hydrodynamics. Okay. So as I said, this is key. So far, this is just a statement about normal hydrodynamics, quantum hydrodynamics. But why can this allow you to build a theory of chaos? Well, the key is because sigma is not a physical variable, it's possible to construct a theory in which it has exponentially growing modes, which are going to be the responsible for chaos, this behavior of the out of time ordered correlation functions. But this is not an instability because it's perfectly okay for sigma to have exponentially growing parts, so long as everything to do with the stress tensor is well behaved. Okay. So in particular, and this is non-trivial, but it's true. Okay, so the first point is okay. In equilibrium, the fluid is at rest and the fluid time is equal to the physical time. What's non-trivial is that it's actually possible to take this action and a general hydrodynamic action, and if you impose that this action has some symmetry, you find it allows you to do what I said and have solutions where sigma of t is growing exponentially in time, but everything else and all correlation functions of the stress tensor are consistent and don't have exponential pieces. So the basic idea is you impose some extra condition on this action to describe a chaotic system, and that condition, which is the symmetry, allows this fluid time mode to have an exponentially growing piece. Okay, and that's the key. And this will ultimately be responsible for chaos. And the crucial point is this is fine and not an instability, because so long as everything is fine in stress tensor correlation functions. So once you've imposed the symmetry and you notice that sigma has exponentially growing modes, you have to go back and use these relationships between the stress tensor correlators and sigma of t. And you find that so long as this exponential growth arose from some symmetry, there's no harm in that the stress tensor correlation functions don't see these exponential pieces. They basically cancel out when you compute the stress tensor, and you don't have an instability of your theory, but you do have exponential growth in this variable, and that's what's going to allow you to build this effective theory. So not an instability of hydro, there's no exponential modes in the stress tensor. Okay. And this is the same story if you have this Felix and Moshe reparameterization modes. It's exactly the same. They have these reparameterization modes. They have the exponentially growing pieces, but those pieces don't rise in the stress tensor. Okay, good. So we're almost there. I've told you that the stress tensor is perfectly consistent. I just need to explain how I get these out of time ordered correlation functions from this theory. Well, the basic idea is if you take some coupling between these external operators, so we have some coupling between these operators and the sigma field, which has an exponential growth. And at leading order in 1 over n, you find that these 4-point functions of these operators just correspond to doing tree-level diagrams where they exchange the sigma field to leading order in 1 over n. So you have diagrams where you have two V operators that come together and form a vertex. The two W operators come together and form a vertex, and then they exchange this sigma field. And because this sigma field is going to depend on the propagator of the sigma field, it's going to have an exponentially growing piece coming from the exponentially growing piece in the equation of motion, solution to the equation of motion. And so from this, you get an exponentially growing, you get exponential growth in these 4-point functions. Okay. So that's the basic idea, but there's one important subtlety I need to highlight because it's important going forwards, which is that at the moment, you find that these types of diagrams contribute, and they do, to both these out of time ordered correlation functions, which I want to see exponential growth in and why I'm doing this, but also other correlation functions, time ordered ones, which shouldn't show any exponential growth with time. That would be an instability if it arose. Okay. So there's a worry, and the worry is that we should only get exponential growth from the sigma field in out of time ordered correlation functions. But the only difference between them and so-called time ordered ones, which are things where I say I take the two W's next to each other and the two V's next to each other. These are kind of standard correlation functions that we'd have computed normally we would never say should show exponential growth, and they shouldn't. That would be an instability. But the only difference between the OTOC and the time-ordered correlation function is actually very subtle. They both have diagrams in which they interact through the sigma field, but it turns out there's slightly different vertices for the time-ordered correlation functions as opposed to the out of time ordered ones. Okay, good. So that's lucky. This vertex structure is the key. And if you write down the details of these vertices, it turns out that the vertex for the time ordered ones is actually simpler. And if you extend this symmetry that you imposed on the action to get the exponential modes, if you extend that to the coupling, you can basically ensure that you can ensure that the exponential pieces, just as they cancel out the stress tensor, they actually also cancel out the time-ordered correlator. Okay. So by extending symmetry to the coupling of sigma to V or W, you find that again, you can make the time-ordered correlation functions have no exponential pieces. There's another cancellation. And this again is exactly what happens in Felix and Moshe's story or in the SYK model. And what happens is that you're left with just exponential pieces in the out of time ordered one, which is what you want to describe a chaotic system. So in particular, what you find is it turns out that the quantity, which is the difference between the out of time ordered correlator H4 and the time ordered one G4, that turns out to be just especially simple if you work out what it is. And it turns out to just be the commutator of this sigma field linearized about equilibrium. And so this gives you exponential growth. There's no exponential growth in G4. So because the difference is proportional to this commutator, you get an exponential growth in the out-of-time ordered correlation function. Okay. So you therefore get exponential growth in H4. Okay, so describing a chaotic system. Okay. So that's a cartoon picture of what happens in this type of effective theory. There was a lot of complicated equations in the paper justifying all this, but this is also the cartoon picture of exactly what happens in the Schwarzian theory and also in these explicit examples as well. It's always this structure which explains how these theories are built. Okay, good. So that's where we'd gotten up to in this old work. I now want to tell you about this new work. So the first thing, which I'm not going to go into a huge amount of detail about because the derivation is actually just very fiddly and requires on the details of these equations, but the result is important. So at the time, it was unclear if this theory we built, so far I've got any value of the Lyapunov exponent here. And it was unclear whether this theory applied only for the maximally chaotic systems like holographic theories due to gravity, which motivated it, or perhaps it could have applied more generally. So we now know that actually the self-consistency of this theory actually requires us to be maximally chaotic. And why is this the case? What is it? What is the condition that forces this to be the case? It's this condition here that we need to be able to extend the symmetry of the theory to the coupling between the sigma field and other operators. So it turns out when you write out the equation that describes what that condition is, what that symmetry is, you find that it involves the two-point functions of these operators as a condition. As a condition of the symmetry involves the two-point function of these operators. And if you now insist or make use of the fact that these two-point functions must satisfy the fluctuation dissipation theorem, you find that you can only impose this symmetry for maximal chaos. So the maximal chaos roughly sets lambda to be related to the temperature of your system, and that the fact that you're forcing lambda to be related to the temperature of the system comes out from imposing the fluctuation dissipation theorem, which involves essentially a reflection in imaginary time and a shift by the temperature. So that's where the temperature enters the game and forces the Lyapunov exponent to be the maximal value. So we now know the theory is only consistent for maximal chaos, which is actually not terribly surprising because in explicit examples of non-maximally chaotic systems, you actually see that other modes other than the stress tensor contribute to the out-of-time ordered correlator. So you wouldn't expect to be captured by maximal chaos. Here we've shown that this hydrodynamic theory never captures any non-maximally chaotic systems. Something different must happen in them. Okay, but this theory it only works for maximal chaos. This is required for the consistency of the coupling of operators to sigma to be consistent with the fluctuation dissipation theorem. Explicitly, I mean the symmetry condition that forces there to be no exponential growth in the time-ordered correlation functions. That's only consistent with the fluctuation dissipation theorem if we have maximal chaos. So that's not necessarily a bad thing. I think it's something everyone suspected all along, but it's good that the theory actually predicts it. The second is this suppression of commutator squares, which is, I think, much more surprising. And initially we were I was quite worried when we noticed this happened. Okay. So I want to explain this suppression, and I'm going to therefore write some equations out that are a bit long, look a bit complicated because there's some notation, but they're just added some notation. So I want to talk about, we've seen that these out of time ordered correlation functions, H4, have exponential growth. But now we want to say, suppose we compute one of these commutator squares in our theory, which I started with at the start. So if you remember, I said what we want to look at is the commutator between W and V and square it and take its average. So let's do that. And now let's just consider the times of each operator to be in principle different. But at the start, I had T1 and T2, the V operator times, to be 0, T3 and T4 with T. Let's assume they're still close to those values where T is very large, but they can in principle be different. They don't have to be exactly the same time. Okay. Well then, in a bit more detail, what I said on the first slide was that if you expand these brackets out, you get the sum of two out of time ordered correlation functions, which I'll call H4 and H4 tilde. And then you also get to subtract off two time ordered correlation functions when you expand these brackets. And I'll write out what these are okay, I'll write this quickly because exactly what these are with these operators is not too complicated. You could expand the bracket, but H4 is WV, WV. H4, write H4 tilde in the top right. H4 tilde is the other time ordered one where I instead go VW, VW. And then we have two time ordered ones. So if I just check my notes, so I know which way round this is. Okay, as I said, the details of this, exactly what I'm writing here is not crucial, but the fact that I can expand this as the sum of two time ordered and out of time ordered ones is important. Okay, good. So this is what you get. As I said, in this theory, if we compute earlier the difference between H4 and G4, okay, so that actually appears here in this out of time order, in this commutator square as two of these terms is H4 minus G4. Well, that I said earlier is very simple in this theory. It's just essentially the commutator of this epsilon field. Oh, sorry, I've got my brackets in the wrong order. And if we remember, this was what was giving us some exponential growth in H4 minus G, in H4, the out of time order correlator. If I now compute the other two terms that appear in this commutator square, I have an H4 tilde minus G4 tilde. It turns out if you compute that using this theory, and it's not actually, it's quite easy to, you can see this diagrammatically quite easily once you understand how to compute these correlation functions. This is just always equal and opposite to the term, to the line above. So it's always minus this commutator. Okay. And so, okay, it has a term that's minus exponentially growing. So what do you find? Well, you find that if you compute this commutator, as I said at the start, it's actually, okay, everything I've said is at leading order in 1 over n. It's actually 0 at leading order in 1 over n. For instance, these exponential pieces precisely cancel against each other. It's actually stronger than this because this doesn't actually rely at all, this discussion, on the form of this propagator, of this commutator of the epsilon field. Okay. And so at the moment, I don't need to actually use any features of the action describing this epsilon field and its dynamics. All I do is I assume I have operators that couple to some field. Okay, there might be there's perhaps an assumption on the form of the coupling. But the moment you write that down in our theory and compute these commutator squares, it's identically 0 at leading order in 1 over n, regardless of the dynamics of this field you're coupling to themselves. So this even if there aren't exponential pieces, whatever's going on in this commutator, it's got to cancel when you compute the commutator squared. And this is identically 0 at leading order in 1 over n. And I think it's when I first saw this, it was very surprising, and you really can't get away from this in this type of effective theory. If you just assume you have some coupling between your operators and some collective mode on a Schwinger-Keldysh contour, and you compute this, this is just zero whatever you do. And so I think it's the fact that we have this effective description to a coupling mode, it's sort of an inevitability, it seems, that you get this result. Okay. So just to further emphasize this, it's also true, one thing you might try and do is that you might think, okay, well, let's try and come up with another correlation function where I separate the commutators in imaginary time, maybe to regulate them in a different way. So that should be a V2, sorry. And if you do this, you find that, okay, you shift one commutator in imaginary time by an amount I theta. This is zero again for any theta. And also we expect in higher dimensions, again, it should just immediately follow as a result of it's very robust. It's basically a consequence of just having a coupling to some mode. You automatically get this. Okay. Good. So as I said, when we first noticed this, I was quite troubled because we claimed we have this effective description of a chaotic system, and we were rightly, I think, very pleased when we found, okay, we could consistently get exponential growth in the out of time ordered correlator. But then normally when people discuss chaos, the first thing they do is they often discuss these commutator squares, and they always write down that it has this exponential growth at leading order in 1/n. And I hadn't at the time seen anywhere any discussion of the fact that this doesn't happen in maximally chaotic systems. Okay, well, in our model anyway, that this wasn't happening. We were getting zero here. So the solution is that I've told you two things. One, that our theory is a system of maximal chaos, and two, that this commutator square vanishes. Both emerge as consistency and predictions of this theory. But the point is that those aren't unrelated. That's really the same statement. Okay, and in particular, if you go back and look at results of this commutator square in maximally chaotic systems, you'll find they do indeed have this suppression. In particular, in holographic theories, due to classical gravity, this commutator square is always identically zero. That's something we've now been able to prove, and it will always be zero. And so this certainly isn't a bad thing at all that our theory is predicting this. This is a property of maximally chaotic systems, and it comes automatically out of our theory, and really just the assumption of some coupling to a collective chaos mode. Okay, good. So as I said, our theory gave us this suppression of the commutator squares. And rather than this being a negative thing, it's actually something I want to argue. It's really a sort of one of the defining signatures and properties of maximally chaotic systems is that they have this cancellation between the two out of time ordered correlation functions, so that this commutator square is suppressed. Okay. So we want to really emphasize this as one of the key signatures of maximal chaos. And as I said, it emerges immediately out of this effective theory. And while it's not really been discussed, apart from a few cases I'll mention, it is implicit. If you go back to previous results and look at their answers, you'll see that this really does happen. Okay. So in the final part of this talk, I want to make this more explicit.
Mike, can I ask a philosophical question?
Yeah.
So the statement is, I have suppose I have some system, and I know that the system is chaotic.
Yeah.
Your statement is, if I go ahead and compute the commutator squared, and I find this kind of cancellation, then without calculating the Lyapunov exponent, or the leading Lyapunov exponent, I should be able to say that that system is maximally chaotic. Is that correct?
Yes, certainly in a large N system, yes.
Okay, and then if I find, in addition, that no, sorry. If I then find that the system is maximally chaotic, is the statement then that this encodes some kind of quantum hydrodynamics in some way?
So
and is that a generic statement?
I guess they're slightly unrelated statements. Yeah, so I guess they're slightly logically separate statements, aren't they? But yes, I would say that if you find you've got a system that is maximally chaotic, then okay, it might not be true for every maximally chaotic system, because there could be some strange examples that aren't like these types of many body systems and stuff. But say you have like, if you say you had a many body system like a field theory or something like that, and you found it was maximally chaotic, then yes, I would say that means that the chaos is coming from the hydrodynamics. Yeah.
So if
in principle,
yeah, I'm trying to work out.
In principle, there should be an effective field theory like this that could describe it. How easy it would be to construct is another question.
Right. I guess I'm trying to work out if there's an if and only if lurking somewhere in there.
So let me think. So
because if I have maximal chaos,
I don't think there's an if and only if in that. I don't think I can prove that all maximally chaotic systems have to have a hydrodynamic description. Because it could be that there was another thing it's in principle possible, logically possible, there could be another explanation for why the commutator squared vanished in a completely different framework.
Right. I mean, so Alexei Kitaev gave this talk, I want to say end of 2018 at the Institute, where he was talking about near coherent.
Yes, so I'll talk about that in the next slide, if that's okay.
Okay, cool.
Yeah,
sure.
It's exactly related to that. Yeah.
Okay, good.
Yeah, it's
good.
Exactly
cool.
that. So yeah, so it's exactly that. So the first thing I'm going to make, first let me just say a really dumb statement, a simple statement. So just the simplest way you could check this prediction of the commutator squared vanishing is, let's take the simplest example where someone could compute this, which is, let's take the theory described by the Schwarzian theory. So if you take the results from the Maldacena Sanford Yang paper, where they computed for the Schwarzian theory these correlators for holographic theories dual to ADS2 gravity. Okay, so their results are Euclidean, but you could analytically continue them to get all these 4 different correlation functions, and you can add them up, and you will indeed find that they're identically 0 in that theory, and all pieces cancel, not just the exponential parts of these correlation functions. Every single thing in all these correlation functions, if you add them together in this form to get this commutator squared, the answer is 0 in the Schwarzian theory. Okay, good. So as Jeff was saying, the one place this has really been discussed before is in a talk by Kitaev. So Kitaev gave a very nice talk, at the Institute, and I think it probably was in 2018. It's a really nice talk, in which he gave a talk based on, I think it was called Coherent versus Incoherent Scrambling, or something along those lines. So he has a separate argument for why this commutator square vanishes, which is, and had also emphasized it as being something that happens in maximally chaotic systems. But I don't think that many people are that aware of this argument, but it's basically based on analytic properties of the outer time order correlation function. So the argument was, roughly speaking, something like this. So Kitaev proposed an ansatz for the OTOC for a 0 + 1 dimensional system, a general ansatz for models that are a bit like S2K or large N systems. So the ansatz is as follows. The key features are the following. So it has some overall constant, which is some real constant. The key part is it has some non-trivial phase, which depends on the Lyapunov exponent. Okay, so this is the key thing. And then it has an exponentially growing part, which describes the exponential growth that we've been talking about, just symmetrized amongst the arguments of the operators. And then there's some vertices, one for the V operator and one for the W operator. These aren't too important. They're just essentially like some 2-point functions. They have similar properties to 2-point functions in that they obey a fluctuation dissipation theorem, which is like a reality condition. Okay. So the key feature in this argument and what's responsible for near coherent scrambling, the cancellation in his case, is this phase here. This phase is basically fixed by requiring that if I analytically continue this correlator so that all operators are spaced evenly around the thermal circle, then that correlation function is just real automatically, and I need to get something real. And given that these satisfy some reality conditions, that just picks out this phase. So this phase is fixed by analytic continuation. Okay, good. So now you can say, okay, let's compute the commutator square. The way we can do that is to compute this other outer time ordered correlator and add them together. And there's a cute trick you can use, which is that the H4 tilde, this other outer time ordered correlation function, is the same as the first one, but if I take the complex conjugate and swap T1 and T2 and T3 and T4 around. So if you do that with this expression above, what do you get? Well, it's not too hard to see. So you still have the overall constant. The important thing is the phase gets flipped. You still have the exponential growth. And it turns out the fluctuation dissipation theorem conditions mean that if you do this operation on these vertices that take their complex conjugate and swap the time argument around, the fluctuation dissipation theorem is precisely the condition that doesn't change. Okay. So what's the point? Well, these two out-of-time ordered correlation functions are the same. They just differ by this phase. And precisely when the Lyapunov exponent is maximal, this top one in H4 is an I and the one here is a minus I, and they precisely cancel against each other again, just as we were seeing in our hydrodynamic theory. So in particular, if you compute this C4 in this theory, okay, what you get it's 2C, and then you get a cosine of beta 0 lambda over 4 coming from adding these phases together, okay, times the exponential growth times the vertex structure. Okay. So the key point is that this commutator square is suppressed relative to H4 by this amount, which is given by 2 cos beta 0 lambda over 4. And that's much less than 1 when lambda is close to this maximal value. Okay? And it's actually equal to 0 if lambda equals lambda max. Okay. So just as in our hydrodynamic theory, we saw that we got this cancellation between these two out-of-time ordered correlation functions in a maximally chaotic system. Here it's emerging solely from analytic properties of the correlation function. So I think that the input here is the analytic structure of this correlation function. In our case, it's a Lorentzian theory, coupling to some Lorentzian mode. So I don't know which is more fundamental, and in principle, they could be two different mechanisms, right, and two different explanations of this. But I certainly think the hydrodynamic description, I think, gives you a more perhaps has a more physical and at least physically explains what this cancellation might mean. Okay.
So sorry, can I just So when, at the beginning of his talk, Kitab was trying to give some intuitive understanding of what coherent scrambling versus incoherent scrambling was, right? And the intuitive picture that he gave was you have a glass of water and you have some ink that you drop into the glass of water. And if you just leave the ink there, then it kind of dissipates and disperses into the water, and eventually, it'll blend into the water. But you can accelerate that process and scramble the ink by stirring it in which case you have some kind of turbulent mixing of the two fluids, essentially. And I've always kind of felt like that is the hydrodynamic description, you know. So maybe it's consistent. I don't know.
Yeah. So I have to say I think they possibly are consistent. I'd like to talk to people about this, because I think that's the point. I think trying to understand what this cancellation means is important. Like I don't understand how this relationship is. Katayo's argument was related to his picture, although I do think the name coherence quite appropriate given that there's the cancellation between the two phases. So I quite, maybe that's why the name coherent came from. But yeah, we thought about we did think a bit about whether we could relate our picture to that picture, but we didn't particularly come up with anything sharp. But it would be nice, it would be very nice if there was a cartoon explanation of why hydrodynamic mode should be thought of as coherent in that sense. Okay, so I'm out of time, so let me just end with saying one final thing, which is just telling you that something is true, which is that we proved that this commutator square is actually identically zero in any holographic system dual to classical gravity. Okay, so again, in holographic theories dual to classical gravity, that's a maximally chaotic system. And what you find is that the outer time order correlation function, okay, so it's maximally chaotic. And roughly speaking, the reason this is zero in holography is what happens if you're familiar with the gravitational calculation of this OTOC. Is the way you compute it is through some gravitational scattering process, through some bulk scattering process between two particles. And the key thing you need to compute is what's called the phase shift for this bulk scattering process. So it turns out that if you ask what H4 is in terms of this scattering, this phase shift for the scattering amplitude, roughly speaking, the correlation function H4, the outer time order correlation function, is just proportional to this phase shift. Whereas this commutator square, you can show, and we proved using kind of a similar trick here with taking complex conjugates, actually turns out to be proportional to the imaginary part of the phase shift. So what happens is that in classical gravity, the phase shift is always real. It's just the on-shell action of a shockwave solution. And this fact that the gravitational scattering is real just automatically means that this commutator square is identically zero. It's just always identically zero if you have a theory dual to classical gravity, which is a maximally chaotic system. And so again, you see that this is again happening as you might expect coming from our effective theory. To get a non-zero commutator square in holography, you have to include string theory scattering between the particles in the bulk. That does two things. It reduces the Lyapunov exponent, and at the same time, the phase shift gets an imaginary part, which means that this commutator square becomes non-zero. Okay, and so again, you can study the suppression of the commutator squares in classical gravity, and you see when it's the gravitational interactions that are important, i.e. the hydrodynamic interactions, you get, again, this cancellation, and you get that this commutator square is zero. Okay. So let me end there, because I've probably said enough, but let me know if you have any other questions.
Thank you. Thanks, Mike. That was a really nice talk. Any questions? If you have a question, you can just unmute yourself and ask it. Anyone? No? Okay. Thanks, Mike. That was a really nice talk. I very much enjoyed it. I forgot to mention that the talks are recorded and uploaded onto our YouTube channel, if you're okay with that.
That's absolutely fine. Yeah.
Cool. Great. Well, thank you very much. I look forward to seeing where this program goes from here.
No, well, thanks for the invite. It was fun. Nice. It's always nice to speak about some research. I've, been a busy few months, so.
Yeah, I'm sure.
Cool. Okay. Thank you, Jeff.
Great.
Bye, everyone.
Thanks a lot. Bye-bye.